Okay, so this is going to be the prep lecture for section 4.2 on concavity. So let's get started. So one of the things we need to do first is think about what we remember about just how functions increase. So this is what we learned from the first derivative. Let's try out a few things here. We know that when the first derivative is positive, that means that the function is increasing, and we know that the graph is rising. Now, it can rise with a couple of different shapes. It can be straight, or it can be curved. And today we're going to talk about the curve. We know if it's negative, the function is decreasing, the graph is falling, again, left to right. And also the same thing, it can be straight, curved, in either direction. So let's talk about the curve. So there are different kinds of increasing then and decreasing. So we can think of this straight as this would be a constant speed, right? It's a straight line with a constant slope. Let's look at this one. So we have here straight is a constant slope. And let's look at some of the curved ones. If I start with one that looks like this, originally the slope is here, and then it's here, and then it's here. So the slope is actually increasing. So in this case, we have an increasing slope. Okay, let's look at the last option, like this. We start here, and then here, and then here. So the slope, while it's always increasing, is becoming less. So, the slope itself is decreasing. The graph is still rising, but it's rising at a slower and slower rate. So here we are talking about increasing, decreasing, slower rate. So anytime we're talking about rate and increasing and decreasing, that makes us think of derivatives. And so, but now we're talking about how the slope is changing. So because we're talking about a change in slope, change in is derivative, slope is already derivative, so really, if we translate this, we're saying, what is the derivative of the derivative? Can we do that? Well, sure. You can take the derivative of anything, so just because it happens to be the derivative of something else doesn't change that. So we're going to write it this way. Let me just go ahead and define the notation. We know that a derivative is just f prime. This we're going to call the derivative of the derivative is the second derivative. We indicate that with 2 prime marks. Those are not number ones, those are primes. So how do these connect? The second derivative is the derivative of the first derivative. Okay, so let's come over here to this graph. This is the same graph that we had in the last section 4.1 prep video. And so let's just talk about where it's, let's define some things called concavity. We'll look at concave up, concave down, and inflection points. So let's talk about concave, all right, so this is what we need to define. We need to define concave up, concave down, and inflection point. Okay. Well, if we back up to here, and we look at this case where the slope is increasing. It starts out shallow, but now the slope is getting taller, steeper. That means that the second derivative is going to be positive, right? The change in slope is positive. So concave up happens when the second derivative is positive. It's saying that the change in slope is increasing. It's getting bigger. Okay, so where on this graph would that be? Well, here's a place where it's shallow and then it's getting steeper. So this right here is a place of concave up. In fact, this whole piece right here is concave up. This piece, this piece, this piece, this piece. And you notice the shape of those, it's kind of a bowl-shaped up. Some people call it smiling. So it's positive, it's smiling. So the shape is, you can either think of it as smiling or bowl-shaped up. Okay, so let's think about what concave down means. If we come back over here, here's a slope that starts out steep and it starts getting shallower. So it's decreasing. So its derivative is going to be negative. Its derivative of that slope is negative. Derivative of the derivative, second derivative, so second derivative is negative. Okay, so where on the graph would we see that? Here's one where it starts out shallow, and now it's getting, that's kind of strange. It looks like it's getting steeper, but it's getting steeper in a negative direction, so that's actually reducing. So this one, this one, this one, those are all concave down. And you might guess, if we want to think about the shape, that negative second derivative, concave down, the shape is frowning, or bowl down, or anything else you might want to think about. You know, be creative. That would be fun. Okay, so there's some places then where it's one and then the other, and then the other, and then the other. And so just like when we had when we looked at first derivative, and we looked at when it changes from increasing to decreasing, increasing and then decreasing, we have a max there. At that point of change, we can define something. We're going to define this inflection point to be where the concavity changes. Changes sign. So not just, right, so we go from concave up to concave down. So right here at this point would be a point of inflection. Here we're concave down, and then we start sweeping into concave up, so maybe right about there. Here we're concave, the bowl, concave up, and we're getting ready to switch to concave down. So, you know, somewhere where it looks like it gets kind of straight and then turns again. This point is not a point of inflection, concave down on both sides. Same thing here, concave up on both sides, not a point of inflection. One important caveat here is that this has to be in the domain. And the reason that's important is because sometimes we'll have concavity changes across a vertical asymptote. Clearly there's no point there. So the inflection point is where concavity changes sign, provided that it's already in the domain. Okay, so this may start to sound very similar to what we did with first derivatives. We're looking at where things are positive, where things are negative, and where they change sign. And so you might expect that a sign chart would be useful, and you would be right. So let's, I'm going to erase this, and we'll get set up to do some sign charts. Okay, so we're going to look at using a sign chart on the second derivative. So the first thing we're going to do is we'll find the second derivative. We'll do a sign chart. And then we know wherever that second derivative is positive, that tells us concave up. Wherever it is negative, will be concave down. And wherever it changes sign, will be our inflection point. I do need to point out just a couple of things. We, not so much for general functions, but when we start looking at business functions, we need to remember to keep our domain in mind, because typically we don't have negative number of items, negative prices, negative times, and sometimes we'll even find that there's a limit, you know, that the model that we have for our particular business situation is only good for a certain range of values. So we need to pay attention to the domain when we're setting up sign charts. Okay, so let's look at this first example. F of x equals e to the x. Let's think about what that looks like, because you know, you can keep in the back of your mind what to expect. E to the x looks like that. It doesn't come up here at the end. That's an asymptote. So that looks like, to me, that it's going to be concave up the whole way. Looks like it's got that bowl shape up the whole way. So let's check it out. First derivative equals e to the x. Second derivative, again, e to the x. Okay, so if I were going to put anything on the sign chart number line, I need to know where this is equal to 0. Never. So there's no point to put here, which means that any value I pick for x will give me the proper sign. So any value I put in there for x gives me a positive. So that tells me that it's concave up for the whole time. All right, so I guess I'll put that here. So concave up, and we like to use interval notation. As we start putting derivatives and second derivatives, increasing, decreasing, and concavity together in graphs, it's going to be very important to list intervals and to use xy coordinate pair points. So that when we talk about what is the inflection point, we're actually going to list an xy pair because you're going to need to graph that. So you're going to have that information anyway. Okay, so that's one example. Let's do another. G of x, oh, excuse me, ln 1 over x. That's a little more interesting. Okay, so let's review some derivative rules. Importantly, this is ln of, not ln times. So ln of 1 over x, that suggests chain rule. But I see another way to do this one, because chain rule, and then I have to rewrite that. Let's just go ahead and rewrite that in the first place. But ln of x to a power, I can simplify that. So I can bring that negative 1 down in front, and now I have transformed this, which looked a little bit ugly, into a basic. So let's look at g prime is just negative the derivative of ln x, so negative 1 over x. And so we could do a sign chart on this to get information from the first derivative. Let's concentrate on the second. You may want to write this way. We're going to be going back and forth, particularly for rational functions when we're looking at first and second derivatives. Sometimes it's easier to think of it this way to find the derivative, but easier to think of it this way to do computation. So we're going to be going back and forth a lot. So here, negative 1 times negative is positive, x to the minus 2. So I'm going to go ahead and write that this way. Okay, so what numbers go on the sign chart? Anywhere where this, the second derivative, and again, we should label these. I did not label this one, and I should have. Because we're going to be having multiple sign charts, it's a really good idea to label them. So here, anywhere that this is 0, nowhere. Anywhere it's undefined, yes, 0. And again here, maybe a hole or a dotted line, something to indicate that it doesn't exist. But now we need to go back and think about domains. What do I know about the domain of ln x? I can only take the log of a positive number. That means x has to be positive, so I don't have that. So it's really important, again, with business applications also, to remember the part that, because it'd be very easy to just try and plug in some numbers, and you would get some numbers in here, but they wouldn't make sense because they don't exist in the original function. Okay, so if I put in a positive number here, I just get a positive number. So that tells me that, again, this one is increasing, not increasing, sorry, concave up, for all real numbers. Okay, so far nothing very interesting. So now let's do one that will have a little bit more to do. These problems, once we start adding the first and second derivatives and getting all the information from everywhere, can end up being a little bit lengthy to write out. They're not necessarily difficult, just lengthy. Okay, so here's one last example. Okay. So you may be looking at that and thinking, cubics, I don't want to deal with a cubic, that's hard to factor. And that would be true. But that's not what we're interested in right now. Right now we're interested in the second derivative. And you're going to find, if you think about it, that when I go down to the first derivative, all the powers go down by 1. And when I go to the second derivative, all the powers go down by 1 again. So this cube is going to end up being just a linear factor by the time I get to the second derivative. So that's great. That's actually easy. So let's take our time. These are all straight powers, all basics. So 3x squared minus 12x plus 9. Second derivative, 6x minus 12. Very easy. So again, I'm looking to make a sign chart, so I want to set this equal to 0. Different ways to do it, you don't have to factor that. The one advantage to factoring it is that then, so clearly I know then that this tells me that x equals 2 is my 0. The advantage of having it in factored form is that it really is very easy to tell the sign. So here, I'll try 1 and 3. If I put 1 in, positive, negative. And if I put 3 in, positive, positive. And actually, I'm going to erase some of that part. I'm hoping that you're getting to the point where you don't need to maybe write out so much detail and we could just write negative, positive. Because one thing you may want to have room for, or at least leave an extra line for, is to be able, got wrong, try again, is to be able to kind of rough in the shapes. So just like we put arrows for increasing and decreasing on the first derivative sign chart, here we can kind of give some curvature information. Okay, so let's write out, what do we have? We have concave up, wherever the second derivative, let's label it, is positive. So that's from 2 to infinity. Concave down, down is negative. So from negative infinity to 2. In this case, we do have a point, and it is in the domain, because the domain is all reals. We do have a point where the concavity changes. So this will be an inflection point. So the inflection point happens at 2. And again, let's go ahead and get the y value for that, because we're going to have to, at some point, graph that. So we might as well have the y value. So that'd be, I'm going to write that down. 8 minus 6 times 4 minus 24, that'd be minus 16. Plus another 18 is 2, plus 1 is 3. So if I did that correctly, 2, 3 would be my inflection point. Okay, so I think that's it. So the important thing is, this is what you're going to be doing for the prep assignment. You're going to be finding second derivatives, doing a sign chart that's everywhere. Remember, the points are everywhere where this second derivative is 0 or undefined, so numerator and denominator. If it's positive, concave up, negative, concave down. If it changes sign, it's an inflection point, so long as it's in the original domain. Okay, I think that's it. Oh, you're kidding me.